Hey, welcome back. So recently I was reading CBS is going to do a new documentary unveiling the mystery of Satoshi Nakamoto, the mysterious founder of Bitcoin. And personally, I don't really care who Satoshi Nakamoto is. Maybe I know who it is. Maybe I don't. But regardless, I thought I would mess with him a little bit. And we're going to ask a more interesting question today. Why did Satoshi Nakamoto use the Berkeley database? And why is that a more interesting question? Because actually by understanding why the Berkeley database was used in the original Bitcoin source code, we can start to understand really the thinking of Satoshi Nakamoto, but we can also understand some of the influences that Bitcoin had. Bitcoin just didn't come out of nowhere. There was actually a lot of influences by previous systems and papers. And today, we're going to look at that. So specifically, we're going to look at version 0.1 of the Bitcoin source code. I will put it up on my GitHub so that you can have a look at it. It's the earliest version that I could find on the internet. Now, it's not perfect because although it was released in January 2009, of course, Satoshi Nakamoto and Hal Finney worked on this together prior to that. So therefore, I'm not going to be able to distinguish between what is Satoshi's code and what Hal's code is. But I think it's fair to say that most of the code is probably Satoshi's, so therefore we can gain a lot from understanding the code that was written. Before anybody jumps in and goes, Hal Finney was Satoshi Nakamoto, he wasn't. Okay, let's just move on for that for a second. However, the influence that he had both on the Bitcoin code, Bitcoin as an ecosystem, and on cryptocurrencies in general was absolutely significant, and therefore I really think that should be recognized. But let's move on from that and take a look at the source code. So as I said, we're not going to look at all the source code of Bitcoin 0.1. We're specifically going to look at the database code. So you see here db.h. If I just open that up, you can see copyright Satoshi Nakamoto. And then you see this hash include dbcxx.h. Now that tells us that it's using the Berkeley DB underneath there. That include file is a Berkeley DB include. So if you've never heard of Berkeley DB before, it was created in 1994 by Margot Seltzer. Again, another example of amazing female technical pioneers that we have in computing, and Keith Bostick. And they created it in the University of California, Berkeley, hence the name Berkeley DB. Now, Berkeley DB really was a pioneer in the industry. It was, up until 10-15 years ago, the most popular embedded database. It was a key value database, so it is one of the original NoSQL databases, and it was designed to run on BSD, which was Berkeley's flavor of Unix. And of course, since then, BSD is not really popular because things like Linux, of course, is much, much more popular than BSD. But at the time, super, super popular operating system, and Berkeley DB was the de facto standard for an embedded database. Now, of course, that changed when Oracle bought Berkeley DB, and therefore it all got complicated with the licensing, and therefore things like SQLite, and then of course in the more highly transactional recoverable databases, LevelDB and RocksDB became the more popular option. So Berkeley DB is not really used that much, but its impact on the industry was incredible. So as I said, Berkeley DB, popular until 2013. It was open source, transactional, fast, highly recoverable. That was its big thing, right? Industrial strength database, right? It could recover transactions. If your server went down or your device went down, then it would be able to recover the transaction log. And that's one of the key capabilities that it had. It had things like write-ahead logging so that you could do transactions and you could recover the database. Now, if you start to think about something like Bitcoin, where it's a transactional system and you're going to be replicating transactions across the blockchain, etc., that high recoverability is a key feature that you're going to need in a database. It's cross-platform, it's fast, it's written in C, it can handle up to 256 petabytes, so it's scalable, it's industrial strength with the write-ahead logging, it's got that recoverability, it's open source. So you're probably wondering yourself, Chris, why are you even asking the question then? The way you've just explained this makes Berkeley DB seem like the absolute natural choice for a database in 2009. And the answer is, no, it wasn't. Unless you know what you're doing, I don't think you would have naturally picked Berkeley DB back in 2009. I think you would have done what you would have done today, and you would have leaned towards something like SQLite. But I think in order to pick Berkeley DB requires either a level of knowledge of transactionality, recoverability, and what you need to do and how databases work, or it would have been influenced by another project. I don't think it's your natural first choice. Your natural first choice would be something like SQLite. So you're probably thinking to yourself, good point, Chris. Why didn't Satoshi Nakamoto pick SQLite back in 2009? Just like it is today, it was the most popular embedded database in the world at that point. It is open source, it is fast, it's self-contained. It's written in C, just like Berkeley DB is. It does have transactionality. It is cross-platform. It's got a max size of 281 terabytes. It was created in 2001, so it was around. So why wouldn't you have picked SQLite? Well, there is one flaw that SQLite had in 2009, is that write-ahead logging didn't get supported until version 3.7, i.e. 2010. So from a recoverability perspective, SQLite was not that great. So that meant there was a possibility that it could lose transactions or not recover transactions. That wasn't implemented till 2010. So although SQLite is a great database for doing lots and lots of stuff and being fast, etc., but in 2009, it just wasn't suitable. And therefore, Satoshi Nakamoto had to know that. And if Satoshi Nakamoto didn't know that, then Satoshi was being influenced by other code. But either way, this knowledge of databases in Satoshi Nakamoto is obvious, right? You need to understand transactionality, you need to understand two-phase commits, you need to understand write-ahead logging, and you need to understand the capabilities of databases, and you probably need the influence and understanding of older systems. So let's come back into the code and actually look at some of the code that was implemented by Satoshi Nakamoto. And again, I don't know if this was Satoshi's code or if this was Hal's code, but I'm fairly sure that this is probably Satoshi's code, or more likely it was code that was influenced by another solution. Okay, so we've already covered the include file for Berkeley DB. So first thing is you see this class CDB, and that's really a base class for this Berkeley database that everything else is going to inherit from. Why do I need to inherit a base class here? Because actually there's multiple databases that are going to need to be implemented. So there's this transaction database, which again, you can see there is inheriting from this base CDB class. And then there's a review database. So in the original Bitcoin code, there was this idea of the ability to review transactions, right? And you could, as you see here, you can read reviews, read users, write users. And then there's this sort of idea of a marketplace. And then you can see the database there, market.dat. And then in this case, there's a reviews.dat, so different files, so a different file per database. There's an address database. I'm assuming that so that you can store different wallet addresses there. And again, you can see the kind of write address, load addresses. And then your wallet DB, right? So, and that's under wallet dat. Now, a bunch of these disappear over time. The wallet one is the sort of the key database, but they're all inheriting from this CDB. So hence why inheritance and object orientation was important, so that you could do the reuse. So now that we've got that, we're going to come back to this CDB class. And what we will do is specifically look at some of the implementation code for CDB. So if we look here, this is the actual constructor for the CDB base class. And again, you can see that this is responsible for either creating or opening the database for the derived class. So based on whether it's a wallet DB or whatever, it's just got a bunch of common code. Now, if I just scroll down a bit here, here's the database open code. And again, you can kind of see create, init lock, thread, private, recover, and then you've got this comment here, Satoshi's trying to do some login, causes corruption. So you start to get the idea very early on, right? Without even understanding Berkeley DB too much, you can see that this idea of recoverability and corruption is very much on Satoshi's mind. So to come back to this question of why Satoshi didn't use SQLite, then Satoshi, just based on these comments, would already understand that SQLite is not going to have the recoverability that need, and therefore you can see this sort of they would be testing for corruption, and therefore in this comment where they were already got an issue with corruption, then SQLite is just gonna fall over, and Satoshi knew this. So there is a level of expertise about recoverability, about transactionality in databases already coming across here. So Satoshi understood Berkeley DB and understood how to work with this code. Maybe that's something that was learned over time, or maybe it was influenced, but there is a knowledge there. Next thing that I want you to look at here is you see this DB flush. So what they're trying to do there is just flush any of the log data. Remember I said about write-ahead logging. What they're essentially going to do is, as transactions are built up on that log, they get flushed out into the data file, so that's going to be stored, and then that's a periodic thing as time goes by. Now, as you understand here, and I think this is super important, there's this bull shutdown there. So Satoshi wants to understand whether there's a shutdown happening or not, to make sure that when we shut down the database, it's happening in a controlled fashion, and whatever's in the log file gets written to the database. And then you can start to see things like transaction checkpointing occurring. This is somebody who understands databases there. And again, it's wrapped into this critical block. I mean, I'm not going to look at the critical block code there, but you can sort of get the idea there that this is being wrapped into a protected piece of code, so nothing else is going to get in the way. I imagine it's stopping other threads getting into this. Is going to handle all the try catches, etc., and deal with the transactionality properly. So therefore, and then eventually on the shutdown, if it is a shutdown, it's going to close down the database once all the file usages are done. So, and if we take a look at these critical blocks, Satoshi uses them quite a bit. Satoshi's using it on the DB flush, which is used on the shutdown. You see that the critical block is being used here when we're closing a database as well. Again, this is decrementing the file usage there. And then again, even on the opening of the database, you see all of this is being placed within a critical block. So if I just open up the critical block, I would expect the critical block to be dealing with things like threading, so that different threads can't come in at the same time and cause corruption. I would expect this to be dealing with how to handle failures, try catches, exceptions there. And again, if I look at this, you can see this already that's occurring. So you see this f critical block once equals true. It's in a for loop. And then there's an assertion break caught by critical block. So you can and then critical block once equals false. So you can get this idea from just looking at this, that if another thread tries to attempt to come into that block, then the f critical block once will be set in that sense, and then it's going to be able to kick off that assert, and then it's going to be able to kick that out. So this idea of criticality is somebody who understands threading very well and transactionality. Again, it's not necessarily hard stuff to get around. Anybody that's done computer science and understands how threads work, etc., and how databases work, that will understand this. But this is somebody who understands how database works, and they understand Berkeley DB very well. And again, once you get into the knowledge that Satoshi clearly has, then it's clear Satoshi would always have picked Berkeley DB, and then something like a SQLite would never have been picked. Now, I did say that Satoshi was massively influenced by other solutions, and the one that we're going to look at today is digicash. Now, digicash was created back in sort of 1989. It was created by David Chaum, who was one of the big players in cryptography as it was. In fact, he wrote a very, very famous paper on blind signatures. I'm not going to go into that today. I think that's a discussion for another time. And again, a lot of people have discussed that from a kind of Bitcoin white paper perspective and the influence that David Chaum had, but I think it's more interesting to look at this from the influence of a digicash perspective. So digicash actually went under probably in around, I think they went bankrupt around 1999, which I think is the key thing. And then they were all of its assets were acquired by InfoSpace, I think eventually in 2002. So digicash and its eCash technology, I think, was a massive influence. And I'm going to show you where Berkeley DB comes into that in a second. So I've gone back to the Wayback Machine, and I've just put in digicash, and then you can see there's a captured version of the digicash website. And I've captured, I think it was a version in 1997, and you can see electronic payments with eCash. Digicash eCash is a software-based payment system which allows users to send electronic payments from any personal computer to another PC or workstation using any computer network, including the internet. So and again, it was massively popular. People like Deutsche Bank were doing trials with this. Of course, it eventually went under, but this obviously and clearly had a massive influence on Satoshi Nakamoto, but not necessarily in the way that you think. So I'm going to bring up another piece of code, and this is from a solution called Dash-lucra. Now, Dash-lucra, if you've never heard of this before, was actually created by what you call cypherpunks. In fact, you can just do a little bit of a Google here and you'll see this, and you see here, created in, this was published in 1996. This is a version 09 of Lucre. We pronounce it Dash-lucra. The unofficial cypherpunks release of eCash, right? So this is probably quite important. So digicash's solution was closed source, but the API for things like being able to do payments, withdrawals, etc., was public. That was a thing you could see how to do. And what actually happened with Dash-lucra is the cypherpunks, in this sense, decided that they were going to create their own implementation of eCash, and that was this Dash-lucra. And actually, I've downloaded the code for this. So I've got version 0.9 there, but I've also got version 0.81 in front of me. And the reason I picked 0.81 is if I go into the server version, you can see there's eCash.h. And then we can see some names here. So this is, they didn't write the code of this part. This is the header file. But you see Bryce Wilcox, Zuko. So again, probably we could do another video on Zuko at some point. Felix Crows, Marcel van der Pijl, Branko Lancaster, Niels Ferguson. So these are all the digicash employees, which is cool. But then right here is Ian Goldberg, right, from Berkeley. And Ian actually did a lot of the coding for this. And I think this code base, which goes back to sort of 1996, 99, around that sort of period, I think that code base has had a massive influence on Satoshi Nakamoto on the code that they have written here. So this isn't the code of digicash. This is the code that the cypherpunks, including Ian Goldberg, implemented to try and replicate eCash. And again, they were worried that they would broke some of the patents or whatever. Again, that's probably a bigger discussion. Now, if I look at this, there's lots of interesting code. It was all written in C. It's got things like withdrawals, etc. Very interesting. It's got user info. It's got the ability to open accounts, do payments. Again, all of the sort of stuff that you would start to be thinking about if you were creating some sort of e-payment solution or e-wallet type solution. Now, the bit that I'm gonna kind of focus on for a second is there's a database. So you can see under here there's WWallet, WDDB, WCashDB. So we can sort of you can take a look at that. You can see things like coin generations. But let's before we delve into this a little bit more, let's just look at the install file here. And there you go. You can see to compile Dash-lucra, edit and make a file to reflect the location. So you include files for SSL EAY. I guess we could do a video on this at some point because, again, that's something that's used in the Bitcoin code as well. And Berkeley DB on your system, if you don't have them, have a look at it and then do the make. So Berkeley DB is the database of choice for this implementation by Ian Goldberg. So now, if I open up this lucre.h here, there's a few things I kind of want to point out that I think is important. First one is you see this include for db.h. And if I just right click on this and do a go to definition, there we go. We are copyright 1990, 93, 94 at University of California. So that db.h is the Berkeley DB db.h, right? And then you can sort of see all of the implementation of Berkeley DB's header file there. And again, if I go down a little bit further on this file, you will see things like, let's just find DB. So you can see there's the type definition for DB, ECWDB. So that's going to be used across the board there. You start to see sort of the database names, receive.db, payments.db. You've got this idea of wallets getting passed around. So Berkeley DB is a very, very key part of this. So I'm not going to go into too much detail in there, but it's fair to say that Berkeley DB is a fairly integral part of this. It's got things like the ability to handle transactionality, doing locking, etc. So very, very influential in that sense. You can also see this hash include bn.h, which is big handling of big numbers. That actually comes from the SSL-EAY library, which is the sort of precursor to OpenSSL. And again, if I come back into my Bitcoin 0.1 code and I have a quick look in here, you can see there's a bignum .h, which is including from the later OpenSSL bn.h. And again, even if I do a find in files here for SSL EAY, if I do a search for EAY, you can see here in the README, this product includes cryptographic software written by Eric Young, EAY at Cryptsoft, which is where the SSL EAY comes from. So you get this idea that there is a lot of influence that is coming from Dash-lucra. Now, again, this is a good 10 years before Bitcoin was written, so you would expect a lot of that code to change. But I think it's fair to say that Satoshi Nakamoto had that Dash-lucra code and has seen it and has looked at it and was influenced. Now, the code they've implemented for Berkeley DB is far different from what is implemented in Bitcoin side of things, but you can then take the influence of sort of big numbers, bignum.h, etc. also from there. There is a lot of influences coming between the two code, how it does things like locking, etc. So there you go. I think Ian Goldberg's contribution with Dash-lucra is something that really Satoshi Nakamoto has been highly influenced and took a lot of the concepts from that and brought that into the Bitcoin code. Again, I think that should have been called out, right? I think that contribution is just as important as any sort of research white paper. The code is the implementation of Bitcoin, and therefore some of that code has been pulled out and been worked on and then reimagined. And I think that should have been maybe called out. Now, there is another implementation of lucre. So if you were to Google for lucre and look for Ben Laurie, Ben Laurie comes from University of Cambridge. Ben was actually highly involved in Apache SSL, so understands SSL very well. And Ben actually wrote a version of lucre, and you can go to Ben's GitHub as well. It's different from the Ian Goldberg version. It was written later, but it's worth checking that out. So I've opened up the Ben Laurie's version of lucre. Again, I haven't spent a lot of time analyzing this, if I'm honest. You can see there's a lot of Java code in here. There's a bank.java. You can see Ben's written this in 1999, which is slightly later than Ian Goldberg's version. There's coin.java, etc. You've got versions here. Lucre version, copyright 1999 to 2003. And again, there's some C++ as well. So if I go into source, we can go, there's a bank.h. Again, you see stuff like bignum in there, which is interesting. But again, it's a different implementation from both Bitcoin, and it's a different implementation from the Dash-lucra version that Ian Goldberg and the cypherpunks did. So, I think it's interesting. Again, it's an attempt to implement the digicash, ecash stuff. But, again, it's a different approach, Java, etc., as well as C++. Different versions of OpenSSL. Again, great stuff. I think that someone like Satoshi Nakamoto probably would have looked at this code and would have been influenced by it. But I feel that there's a bigger influence from the Dash-lucra version of before. So if I take that into consideration, why did Satoshi Nakamoto choose, Berkeley DB? Then I think clearly Satoshi's looked at the Dash-lucra code before, understands that, either has a good knowledge of Berkeley DB themselves, or has taken that influence of that code and then taken it to the next level and then learned about all the transactionality, recoverability as part of that process. But anyway, either way, I think Berkeley DB, I think the Dash-lucra project, I think digicash has been a massive influence on Bitcoin, as you can see, and hopefully that gives you a better idea of the character behind Satoshi Nakamoto. All right, I'll catch you in the next video.